statistics. And most of the shapes that I'm going to be talking about are anatomic shapes, such as this hippocampus, something that's in the brain, which is yellow here, or this, I probably can recognize the jaw, fancy medical term, the mandible on the right. And we're going to be talking about representation of objects like that, computer representations, mathematical representations, and statistics on populations of them. Whoop, already what do they do now? Let me restart the slides. Reshare. Aha. Let me get my clicker. Okay, so what am I going to do in this course? I'm going to start after this overview with some basic math, some background math beyond what some of you already have. I'll tell you what I'm expecting as a prerequisite in a moment. But I'll be presenting some background math and later in the course, some background statistics approaches. I'm going to survey a variety of shape representations. And so you can see here, the boundary of that hippocampus in gray and a skeleton inside it that is part of a representation via skeletons. We're going to be talking about representations via diffeomorphisms. Diffeomorphisms are smooth deformations. Okay, and so you have a basic object here, such as an ellipsoid. And you talk about how the space containing the ellipsoid is warped to give you the object. And then the shape representation is the diffeomorphism. How that maps. We'll be talking not only of representation of single objects, but of multiple objects. If you think about any part of the body, but let's say the brain, there's lots of objects that make up the brain. Here are two of them, the one on top and the one on bottom. One of them is the hippocampus, the other one is the caudate nucleus. But the point is that you want to talk about not only how to represent the individual objects, but also their relationship to each other. Another way of saying that is how to represent the space between the objects and how they're related. And here you see in the example some links to a special surface that is sort of, it's called the linking surface, and it's halfway between one of the objects and the other of the objects. And we're not going to be talking about just shape representations, but methods of shape statistics. In shape statistics, you have a population of objects, for example, across many individuals, and you're interested in doing the kind of things that statistics do. You're interested in a mean, what does an average shape look like? You're interested in how shapes vary around in the population. You're interested in classification. If you have two classes of shapes, and now you have a particular one, you want to decide in which class, for example, diseased or not diseased, that shape is in. You're interested in hypothesis testing methods. Interested in segmentation. These shape representations and their the shape representations, and the statistics are what a physician calls anatomy. They understand what the shape of a kidney is or what the shape of a hippocampus is, right? and they understand how the various possible kidney shapes are. And so we will also talk a very little bit about segmentation, where as a statistical objective, because to find objects in images, you need to know the anatomy. And we'll see how that works. Statistics of shape involves the fact that the shape properties don't live mathematically in a Euclidean space. Meaning, if you want to talk about the differences between the features of one object and the features of another object, you can't simply subtract the feature and take the square root of the sum of the squares. So this means that there are special challenges in doing statistics of shapes, because you have to be able to do statistics on these curved manifolds, these curved spaces, and we'll be talking about that. Okay, so if you're here, you probably know that we're starting at 3:30 and we'll go to 4:45 each time, and it'll happen on Tuesday, Thursday, except on UNC holidays. I will be announcing office hours for people to come ask questions or talk about, for the people taking this for credit, they'll be doing projects. As I have said, I would like every participator to have emailed me by tomorrow midday. Many of you already have, you don't have to resend, but if you haven't done that, and this goes for the auditors and out on Zoom, as well as everybody who's here, because I want to be able to email you their announcements and other things I want to share. My email address is there. My office phone number is there. You can make an appointment with me and meet with me at an office hour or an appointment time, either in my office or on the Zoom site that we're now talking about, the class Zoom site. And the class Zoom site, of course, is listed there with the passcode that you need if you're going to be getting in touch by Zoom. We're still learning the process of making the recordings in the form that we need them to be. The problem is that we have basically two sources. We have a wonderful camcorder here that has been bought for the purpose. And by the way, if you're in the department, it's intended for use for lots of different uses and not just this course. But we also have these slides, these PowerPoint slides that are being recorded, and they have to be edited together in a split screen sort of format for the recording. We haven't quite learned how to do that yet. And so we're going to, what I'm going to do tomorrow, early afternoon, I'm going to take the list of participators from whom I have emails, and I'm going to send you this slide set and the recording that's being made today as simply part of the email that I'll be sending you. Soon, you'll be able to get the recordings via this cs.unc.edu/shapecom790-6 site. What it will be a catalog that's kept up class by class. Each catalog item will indicate what the lecture was on, and will give a YouTube address. And the YouTube place will have this wonderful recording that we'll eventually make. But we'll not be able to get the YouTube recordings till we can figure out how to do the editings. So at least for this class, you won't find it on that site. if you are a UNC student, you're welcome to take the course for credit. And if not, you can do it as an audit. UNC has a means of recording audits. If you want to have a recorded audit, you can sign up for it. Any questions so far? Okay, what do I assume in background for y'all? I assume you know multidimensional calculus. What that means is basically you know what a gradient is in n dimensions. You know what a directional derivative is with respect to some direction in n dimensions. You know what a Hessian is, which is a matrix of second derivatives, just as a gradient is a tuple of first derivatives. And you know what a Laplacian is, which in Euclidean space is simply the sum of second derivatives in any group of n orthogonal dimensions in n space. So in 3 space x, y, and z, the second derivative twice in y, twice in x, plus the second derivative twice in y, plus the second derivative twice in z, gives you a Laplacian, but it doesn't have to be x, y, z. It can be any orthogonal coordinate system. Okay, I also assume that you know some linear algebra, that you understand what a matrix is, what matrix multiplications are, and that a matrix times a point in space, a vector understood as a point in space where the vector goes from the 0 out to that point, that when you apply matrices to split space that way, they produce linear transformations that are geometric. That is to say, it turns spheres into ellipsoids. And so you need to understand that much, and you need to understand eigenvectors and eigenvalues of matrices, or equivalently of the linear transformations. I do assume that you know that. And then I assume you've had one course in mathematical probability. Okay, and what that means is that you know what a probability density is for single variables, and also joint densities for multiple random variables. That you understand conditional probability densities, the probability density of one set of features given the values of another set of features. That you understand Bayes' rule that relates different conditional probabilities with each other. And I'm going to assume that you understand what the normal probability distribution is, also called the Gaussian probability distribution, the bell-shaped sort of probability distribution. Any questions about anything so far? For those who are auditing, you are welcome to ask questions simply by interrupting. For those here, raise your hand. If I don't see you in a moment, holler. The questions will be played out to the people on Zoom if you're asking here, and the people Zoom asking questions will be played out on the speaker here. So you should be able to hear each other questions. If you're on Zoom and you don't want to interrupt, you can raise your virtual hand. And Nick here has agreed to look at hand raises and raise his hand in your place so that I will call on whoever's asking the question at that point. Okay? Okay, so I really, really want this to be an interactive class. I want a lot of questions. You need to keep up with the lectures. It'll be hard to understand lecture K if you haven't understood lectures 1 through K-1. And in particular, if you have to miss, use the recording to listen to the lecture before, or the lecture that you've missed, and do it immediately. Because as I say, these things are going to build on each other, and you're going to have a hard time understanding later ones if you haven't done the first ones. I'll be giving lots and lots of readings to do. The people taking the course for credit need to do the readings. The people taking the course for audit will do well to do readings. I obviously can't insist. Also for credit, the people at the relatively small number of people who are taking it for credit will have an oral exam, one-on-one exam at the end of the course. And will do a shape either or both of representation or statistics project. My intention is that the project will be a significant project, something that you begin working on within by a month into the course. And that means that if you're taking the course for credit, you need to have chosen your project by then. And that means that in the first month of the course, you need to come have a discussion with me at a one-on-one appointment to discuss what your project's going to be. At the end of the course, there will be a few of these class sessions where each project will be presented. And so that's basically what's going to be involved in taking the course for credit. Come to class, ask questions, do an exam at the end, do a project, and do the readings. What readings? There are, first of all, 4 books that I put on reserve. For those of you interested in this field, you may very well want to buy your own copy of these books, but they are in reserve in the normal reserve place in the, I guess it's at the undergraduate library that reserve books get put at. In any case, the first one is by Steve Marin, who is a, well, I really should have said J.S. Marin. He goes by Steve, but his initials are J.S. Steve Marin, who's a collaborator of mine and a senior statistics professor, and Ian Dryden, and they have recently produced a book called Object-Oriented Data Analysis. And many of the things that we'll be talking about when we talk about statistics are going to be found in that book. The next is a book by Xavier Pennick, who is a senior shape scientist at INRIA Sophia Antipolis in France. Stefan Sommer, who likewise, well, is an expert in shape analysis at University of Copenhagen, and Tom Fletcher, strictly P.T. Fletcher, but he himself has dropped the P, who was a doctoral student here in this department many years ago, and is now a associate professor at the University of Virginia. In any case, they produced the book, Riemannian Geometric Statistics and Medical Image Analysis, and you'll have readings there. Indeed, there is a chapter by Peiser and Marin in that book. The next one is a book by Jung Lee and Seike. I left off the accent on the first E. But anyway, Gabor is a retired former colleague, still at ETH in Switzerland. Jung is at, well, he used to be at Imperial College in London, but I think he's moved to China recently, and I'm not familiar with Lee. Anyway, a book called Statistical Shape and Deformation Analysis, and their book also has a chapter by Peiser and Marin. And then there's the book that I wrote with Khalil Siddiqui, with what can I say? We seriously edited the whole volume, wrote 5 of the, I guess, 11 chapters in it ourselves, but I have to give credit to the authors of the other half dozen chapters as well. It's about the particular kind of representation that I've been doing in my research, namely medial and the generalization of medial skeletal representations. And you will be assigned certain readings in that book as well. It, to my knowledge, is the only, what can I say, book about mathematics and algorithms on these skeletal representations. But this course is not just on skeletal representations. It goes well beyond the kinds of things that I've been doing my own research on. And then there are going to be lots and lots of other assigned papers that I will get. They'll be, you can find them by the web, but I will also make copies of them and put it on my Google Drive site. And so if you go to the Google Drive site, that is under Pfizer at cs.u, what is it? Yes, at cs.unc.edu, the Google site, you will find a site that is shared to anybody with all these papers in them. So you'll be able to read them from there or copy them. I'm an old guy. I don't like to read on the screen. I print them out and read them that way. Okay. So any questions on any of that administrative stuff about the course? Okay, then let's go on and talk a little bit more detail about some of the topics that we're going to cover. We, first of all, are going to be talking about some basic geometry and topology of objects. Okay, so we have here a surface of an object, and at any given point on the surface, there is a normal that is orthogonal to that place in the surface, strictly speaking. There's a tangent plane, which is a best fitting local plane, and orthogonal to that plane, there is a vector, a unit vector that's called the normal. And so we're going to be talking about the normals and tangent directions, because it turns out that normals are much more informative about shape than the points on the surface themselves. Not to say you can want to throw away the points on the surface, but if you insisted on throwing away either the normals or the points, you'd be better off with the normals. And so we're going to be talking about normals as important things, and tangent spaces as well. Beyond the normals, as you move around on a surface, the normals swing. And the way the normals swing and the rates at which they swing are what curvature is about. Normals, it turns out, are first derivative of the surface positions. The curvatures are second derivative information. And we're going to be interested in the curvatures at places on surfaces, like mostly we're going to be talking about surfaces in free space, and they are 2D surfaces in the sense that at any given point you can go in two orthogonal directions, and every other direction is just a linear combination of the two that you've chosen. So we could say it's a 2D surface in 3D. We will be talking about the geometry of those things briefly, right? I have taught a whole course on that, and we're not going to spend a whole course on that. But we also will realize that these feature representations that we talked about for an object, or for a diffeomorphism, or for any of the representation of an object, live on a high dimensional curve space. And then we're going to be interested in geometric properties in that high dimensional curve space. So to give you an example, a here's a 2D entity. At every point, there is a normal, right? So at some selected set of points, you're going to have normal, 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 etc. Right? Normals are unit vectors. Unit vectors live on a ordinary two-sphere, a two-dimensional sphere in 3 space. A unit sphere where if you put the unit vector at the center of the sphere, you have the vector going from there to a point on the sphere, right? And that point can be specified by 2 numbers, a latitude and a longitude, right? And so it's a duple. Every point on the sphere is a direction, if you will, corresponds to a direction. We say it lives in S2, the two-dimensional sphere. So one normal lives on sphere, but now we don't have one normal. We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 normals or whatever. So we have what's called a polysphere, S2 to the 11th. Right, that is to say, S2 cross S2 cross S2, Cartesian product 11 times, right? And that thing, that polysphere, is itself a 22-dimensional surface. And that 22-dimensional surface has curvatures and normals. So we're going to be interested in curvatures not only of the underlying surfaces that we're concerned with the shape of, but also with the curvatures and normals and other properties like geodesic shortest paths on these manifolds representing the object. Okay, we're going to need we'll have a little bit of information on some topological aspects. This object here is said to have spherical topology, meaning you can deform a sphere into it. It is an entity that has no holes. Okay, but donut, bagel, has a hole through it. And topologically different. And it turns out you need to understand a little bit about this idea, how you make, how you think about holes and what the measurements are on them. Likewise, we have objects, but we have parts of space, which is one object and another object. And we're talking about the interior of these objects, in this case in 2 space. We're interested in knowing that there are 2 connected components in that. We're going to say a little bit, carefully define what we mean by connected components. Then we're going to be talking about shape spaces as manifolds. I've already started talking about that. Spaces collecting all the features that we want to talk about when we represent the shape. We're going to be carefully defining what a manifold is, a smooth surface intuitively. And we're going to be defining shortest distance paths on these manifolds, which are called geodesics. You see here an example of an object that is an ellipsoid, right? Which is an entity that is a sort of a squash sphere. It's like a rugby ball where you have 3 orthogonal axes with their respective lengths. One going along this way, one going across this way, and one going from top to bottom. And those are in 3 orthogonal directions, and each one of those pairs of dimensions produced is an ellipse, right? So there's an ellipse going around this way, an ellipse going around this way, and likewise, ellipse going around that way. Anyway, it turns out that the ellipsoid is going to be a very important, very basic shape type that we're going to be interested in. Okay, it is about the simplest non-trivial 3D shape. And we're going to be interested in it, but we're also going to be interested in these geodesic distances between any point on one of these and another point, or here on the sphere from this place to that point. There exists a shortest path. We're all familiar probably with traveling across long distances in an airplane, and they want to go the shortest path from here to London or from here to Beijing or wherever you're going. And these are geodesics, and you will need to know something about what geodesics are. Likewise, when I say shortest distance, it depends on what measure you use, what metric you use for measuring distance. It turns out that the Euclidean metric, which is the one we're most familiar with, where Pythagoras said that from here to here, you take the straight line between them, which is the geodesic, it's the shortest path, and you take the sum of the squares of the differences of the different coordinate values. That Euclidean metric that Pythagorean said you should use turns out not to be so hot on curved surfaces. Because if I want to talk about the distance from here to over there, I want something related to arc length, something rather than the Euclidean distance, which is the distance from this point in a straight line to over here that doesn't stay on the surface. And there are lots of other situations in which you want to be able to talk about distances that don't accord to the Pythagorean theorem. And the ones we're concerned with are called Riemannian metrics. I find it entertaining that Gauss, Carl Friedrich Gauss, who's the progenitor of local geometry, local differential geometry, had a student named Riemann at the University in Göttingen in Germany. And he told Riemann that he was not strong enough in geometry, so he should do a dissertation in that field. And so Riemann did, and developed a whole major development that generalized distance measures. Okay. Anyway, we'll be talking about Riemannian metrics. Boy, how do I get rid of this? Okay, that says shape representation categories. I don't know. We're gonna have to figure out how to get rid of this thing. Interesting. We have 21 people on Zoom right now. I will tell you that so far I've seen people planning to take this course from Virginia, from Pennsylvania, from Massachusetts, from Stavanger, Norway. That's a bit of a major sacrifice because it's 10 o'clock at night in Norway. In where did I say, in Pittsburgh, in Pennsylvania, a couple places, and on, all across the country. I'm really glad that they're all here. In any case, these categories that we're going to be talking about for shape representation are listed here. On the one hand, we have collections of recognizable points that are called landmarks. You see on the hand that's shown there, marked points that are at the fingertips and at the crotch points of the fingers and other recognizable points. Or sometimes the points are sampled in a different way than just being landmarks. But in any case, you have these so-called point distribution models, these collection of positions of points, which are one of the kinds of representations. It's the simplest one you can think of. Okay, just give the X, Y, Z value of each point. It also turns out to be not the best you can do. Typically, these points are on boundaries. So we're talking about representing boundary points, or the points can be connected by, in 2D, by lines between them, or in 3D by little planar tiles that, like you see in this object here, and all the points at the vertices of the respective tiles can form a representation. And that if you connect them and give, say, what point is connected to which one in this mesh, you will get a richer representation than just the points. Okay, and so we'll be talking about these meshes. I've already talked about the fact that normals are very important, so that at each one of these mesh points, for example, you might have not only the point value, but the normal vector there. Surfaces can be represented by sums of orthogonal functions. So those of you who have done some basic math understand the idea that a signal can be divided into sums of sinusoids, sines and cosines, right? And the result is that a single object, like one I've drawn here, can be understood in terms, that X and Y are cyclic variables that go all the way around here. And the result is that X is a function of position of the arc length around this thing, and Y is a function of arc length around this thing, can each be written as an ordinary Fourier representation, as a sum of sinusoids. And it turns out that when you talk about objects in 3D, where you have a surface, you can similarly talk about representing in terms of sinusoidal-ish functions, things that are cyclic the way a sphere is. Okay, so a sphere has latitude and longitude, if you will, and so we'll have functions of latitude and longitude that are basic functions that behave that way. And then objects can be represented as linear combination of those basis, so-called spherical harmonics. And once you do that, the representation becomes the coefficients of that basis. And so this produces, these coefficients produce an object representation, and we'll talk a little bit about those. Another way of representing shape is to take the object and represent it, think of it as being in a space, one higher dimension. So this is a 1D object sitting in 2 space. It's 1D because there's only one dimension that takes one value that takes you around the object. But you can talk about a curve that is 1 unit of distance outside the object. And you can talk about a curve that's 1 unit of distance inside the object. And the original curve is just 0 units of distance from the object. And you can talk about ones that are 2 units of distance outside and 2 units inside. And in general, if you look at any point in the space, you can think about how far it is from the object. And then the representation is that distance, okay? So you have signed in the sense that outside gets one sign and inside gets the other sign, distance functions. And that turns out to be an interesting representation of an object. Now you have a 2D space and every point in the space, or in a computer, it'll be pixelized. And every pixel center point will have its sign distance value. And that's the representation. It turns out that that representation is of particular interest in computer graphics using neural nets. And we'll talk about that later. Objects don't just have boundaries. Objects have insides. Their interiors are quite important. For this object here, the fact is that it's pretty important that from here to over here, the width of the object here is narrower here and wider here, right? That these objects have different widths, and that width turns out to be quite an important feature. And width is a property that involves the interior of the object getting across through the object. And so we're going to be talking about the interiors within objects and the relationship of one point in the interior to another point in the interior, which turn out to be represented by algebraic graphs. Okay, so we'll of course be talking about skeletal models. Those are where my research has lain. We'll also be talking about special places on an object that can be understood as curves. So if you think about this ellipsoid, there is this place on the side of the ellipsoid, which is called the crest. It's the place where it's most sharply curving in some sense. If you look at my hand, along here, there's a crest. And if I didn't have these individual fingers, it would go around here and come around down like there, right? So there's this special curve that's crest, and we sometimes want to talk about crest curves or other special curves on the surface, that are as part of our shape representation. And so we will talk about these special curves. I call them land curves in the sense that land marks are points and land curves are special curves. And it turns out that the mathematical representation that uses curves is called currents, and we'll talk about currents. And then we will also talk about multi-object representations, which will basically involve representations either of the space in which all the objects lie, and that there's an overall deformation of that space such that regions of the original space map onto the respective objects, or we'll be talking about the objects themselves, but also as I indicated earlier, the space between the objects, the geometry of that space. And then there is this very, very popular means of representing shape, diffeomorphisms from a central example. I've used this as an example here, the ellipsoid to an object, but it need not be an ellipsoid. You can take, if you have a notion of a mean hippocampus, you can take a mean hippocampus and talk about how to deform it into this particular person's hippocampus. And then the representation is the diffeomorphism. Okay. I don't know why. You got to get this out of the way. But when I do that, somebody's got to teach me how to get this to disappear. Okay, anyway. I really messed it. Let's see. Here are all drawings.
The red X was not right.
Hmm?
The red X there.
If I do that, that'll help at least. Okay, anyway. So we're gonna be going first about shape representation by boundary points. The important thing if you're gonna do statistics is that the points have to be in correspondence across the examples. You see 3 different people's hippocampi in the upper right of the screen. If you want to do statistics, it has to be that the IJ point on the left one and the IJ point on the middle one and the IJ point on the right one and all the other ones in the population have to in some sense correspond. If I tell you that this is the point on my index finger, you're going to get shape distance wrong because this point is the point on my index finger, right? Worse, if I tell you this point is at the end of my index finger. Anyway, the point is that you need a notion of correspondence, but what the heck do you mean by correspondence? And we'll be talking about that, okay? There are multiple ways of determining correspondence. We'll talk about each of them. If you have a basic object and you have some idea of what its places are, and then you deform it in an appropriately well-designed way into some other object, you can carry its designated points into the other objects. And if you do that for each of those other objects, then the special point on the reference object mapped onto each of them will be appropriately in correspondence. It turns out that skeletal models very nicely capture a way to do correspondence that reflects not only places in space, but things like widths. And we'll talk about that. And then finally, you can take a sort of an information theoretic point of view and ask sort of what is the cheapest way in the fewest number of bits, if you will, to represent the object in terms of these. And when you take the population and represent it most cheaply, as a population, you end up producing correspondence in one sense, and we'll talk about that also. Okay, I've talked about spherical harmonics. In spherical harmonics, you're actually doing a mapping from a sphere onto the surface of each of the objects in the population, and that mapping can carry points, specified points, and regularly spaced latitudes and longitudes on the sphere onto the respective points here, and you make those understand those to be in correspondence. So we'll be talking about spherical harmonics as a correspondence producer, as well as the representation by itself. So here is a surface with its normals shown, and at the tips of the normals, or the tails of the normals vectors, are the points. And you might very well say, let's represent the point, every point, its position X, Y, Z, as well as its normal, which is a latitude and a longitude. It's a 5-2. You could just look at the normals. It turns out that this correspondence question is so thorny that there's been some lovely research by Anuj Srivastava and his students and colleagues on how to get representations that don't depend on correspondence. That where the correspondence is modded out in the same sense of the modulo that you have, if you will, from arithmetic. And when you mod out correspondence, it turns out that you get a normals representation. And so we'll talk about that. Also, I talked about signed distance images that we're going to be talking about. And I also talked about distances that we're going to be on the boundary via Riemannian metrics. All right. Okay, so there's going to be a section on shape representation by skeletal models. There's some mathematics of it that we will cover at the appropriate time. There's a particular form of skeletal representation was designed to be particularly effective to do statistics on. And that's been what my research has been about, is trying to come up with representations on which you can do good statistics. And this is the method that I defined was called the representation that I defined was called SREPS, is called SREPS, and it involves at every position, it involves a skeleton, which is sort of a collapsed version of the object. Think of my hand, you collapse from this side inwards, collapse from this side upwards into the object, and you come to something in the middle that is the skeleton. And for every point on the skeleton, you have a path that goes, a vector that goes from the skeleton out to the boundary. We call those spoke, such a thing as spoke. And the length of the spoke is the half width of the object. The coloring in this particular diagram is an indication of how wide the hippocampus is at that position. It turns out to be powerful to understand the skeletal representations as transformations of an ellipsoid, which has the very simple skeleton. An ellipsoid there's my ellipsoid. Its skeleton turns out to be an ellipse stuck on a planar ellipse stuck halfway between the top side and the bottom side of the sky. And then when you talk about appropriate diffeomorphisms from the ellipsoid to the object, you will carry properties, geometric properties, and can understand then what that diffeomorphism from the ellipsoid is. One of the things that is particularly interesting is so-called fitted coordinate systems. On a surface in 3D, you have a normal, which is a coordinate, and you have two other coordinates in the tangent plane, right? So if I have a coordinate here, the normal, and I have a tangent plane like this, and I have one here and one here, I get three orthogonal unit vectors that form a coordinate system. And the wonderful deal is, if you now take that so-called frame, a coordinate system, and move it around the object, the fitted frame, the transformation of that fitted frame is what curvature is about. Well, the same idea can be applied to the interior using the skeletal idea. You can find special directions in 2D